Welcome to the exciting illustration of how a fault may actually behave as plates move in different directions across the fault. So what you have here is a little model of foam. So you've got one block here, and in between these we have a fault which has been lined with a piece of plastic to provide a little slippage surface. And so what we're going to do is to turn this crank, which will be pushing this side that way relative to this side. And we'll see that the deformation doesn't occur continuously, but it occurs in discrete events called earthquakes, or perhaps sponge quakes in this example. So let's start off by first initializing the system so that we have just had an earthquake. And we're going to measure the deformation across this line. So let's go until we get a movement. Building strain. Oh, when is it going to go? Oh, there we go. Earthquake. Now, from this point, we're going to measure the deformation. So the starting point then is now at 14 millimeters. Okay, so I'll turn the crank. You can think of each turn of the crank being 1 unit of time, let's say a year in this example. And so there's 1, 2, 3, 4, 5, 6, 7, 8. Ooh, at about 7.5, we got the first movement. And now let's keep track of the deformation. And we get about 38 centimeters. Okay, so you want to think how much slippage occurred? Well, we had a starting point at about 14 millimeters, and here we've got 38 millimeters. Now let's turn the crank some more. So we're at 7.5. So let's take it to 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Ooh, that one went at about 17. And our total displacement is now up to 63 millimeters. Okay, so that was the second earthquake cycle. So let's keep going. And we go 1, 2, 3, 4, 5, 6, 7, 8. Whoop. That was at about 7 3/4. And our displacement is now up to 83 millimeters. Okay, so there's 1, 2, 3, 4, 5, 6. Okay, so that was at 6.5 turns. Our displacement is now up to 97 millimeters. Okay, let's keep going. And we go 1, 2, 3, 4, 5, 6, 7, another 7.5. And we're at 116 millimeters. Okay, let's do one more. Okay, 1, 2, 3, 4, 5, 6, 7. Okay, so that was 7.5 on that. And our displacement is up to 137 millimeters. Well, you want to now think about this, and you say, how do I consider my data? Well, what did we see? We've seen a continuous movement. Well, actually, it's been a movement in steps, but it's generated a certain total distance. How do we get the average velocity? Well, let's see. We know that velocity is distance over time, so if you just plot the distance, the total distance that we've moved at various steps of movement as a function of the total number of turns that we've had, then you say, oh, from that, I should be able to get delta D over delta T, which gives us a velocity. So think about plotting this, and you might take a look at the slope. So with that, we've seen our earthquakes, and plate motion is stopped for the moment, so have fun plotting.